The headline screams that x86 has won the PC war against ARM, sparking panic among engineers betting on the future of autonomous robots. But this narrative confuses desktop dominance with physical reality. For a robot moving in the real world, raw clock speed means nothing if it melts or drains its battery in minutes. Today, we separate the marketing hype from the thermal and power constraints that dictate what an intelligent machine can actually do. The story begins with a fundamental misunderstanding of where computers live inside robotics systems versus where they sit on your desk. When news outlets report on x86 winning against ARM, they are measuring performance in laptop-class benchmarks for running Office suites or compiling code. These tests show that while the AMD Ryzen 7 processor can outperform an Apple M3 chip in raw branch-heavy computational tasks, this advantage evaporates when we shift from a stationary screen to a moving machine. The critical differentiator is not how fast you can calculate a number, but how much energy it costs to do so, and what happens when that heat builds up inside a sealed chassis with no fans. Consider the power consumption required for continuous operation. Comparative analysis of laptop-class processors demonstrates that while x86 chips may lead in peak throughput, ARM architectures achieve a reduction in energy consumption ranging from 5.82 times to 6.38 times during matrix multiplication and algorithmic workloads. This is not a minor efficiency tweak. It is the difference between an hour of flight time for a drone or 12 hours of locomotion for a legged robot. In autonomous systems, battery longevity dictates operational viability far more than peak clock speeds ever could. If you pack x86 architecture into a mobile platform designed to navigate uneven terrain, the legacy power delivery overhead creates immediate thermal bottlenecks that force complex active cooling solutions which simply do not exist in compact robotic forms. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This brings us to the first major constraint: the failure of traditional cooling methods in harsh environments. In warehouse-scale migrations and planetary analogs where dust is a constant threat or sealed enclosures are mandatory for safety, x86's higher thermal design power forces reliance on fans that eventually fail. The complex instruction set decoding inherent to x86 introduces latency spikes during real-time sensor fusion, creating unpredictable behavior when the robot needs instant reaction times. Conversely, ARM's RISC simplicity provides deterministic execution critical for low-latency control loops in dynamic robotics. This allows systems to operate reliably without fan failure modes that would otherwise cause a dust-clogged motor or overheated processor to shut down mid-task. The passive thermal profile of ARM enables reliable operation where x86 simply cannot survive the physical environment it is meant to navigate. The narrative also overlooks how these architectures handle the continuous load of legged locomotion and sensor fusion. Energy efficiency benchmarks show that ARM architectures deliver superior performance per watt ratios, specifically for tasks like maintaining balance or processing LiDAR point clouds during movement. These are not occasional bursts, but sustained loads where x86's legacy power delivery overhead creates a heatsink problem that no amount of software optimization can fully resolve without adding weight and volume to the robot itself. When you remove the heavy cooling hardware required by high-performance x86 chips, you free up significant payload capacity for batteries or tools. This trade-off is why ARM has become the mandatory architecture for next-generation autonomous systems where every watt counts towards survival rather than just raw computation speed. Yet we must acknowledge that these efficiency gains stem from system-level integration and power management mechanisms rather than inherent instruction set superiority alone. The available research explicitly limits its scope to laptop-class systems, meaning there is a knowledge gap regarding benchmarked performance per watt data specifically for autonomous legged robots or mobile manipulators in the field. We are seeing theoretical soundness based on thermal profiles that suggests x86 will remain a legacy liability for mobile robotics, but we lack direct empirical data confirming ARM's total dominance across every type of robotic hardware currently deployed. The transition away from x86 is driven by these physical constraints rather than a sudden market shift in software compatibility or developer preference alone. The PC war narrative fails because it assumes that the best chip for your spreadsheet is also the best chip for your robot. In reality, an intelligent machine operates under different laws of physics where heat dissipation and power density are the primary drivers of design. The complexity required to decode x86 instructions introduces latency spikes during real-time sensor fusion that can destabilize a balancing humanoid or cause a drone to crash in high winds. ARM's streamlined architecture avoids these pitfalls, providing the deterministic timing necessary for safety-critical control loops without sacrificing the computational power needed for navigation and decision-making. This is not about which chip runs faster on paper, it is about which system survives 10,000 cycles of operation without overheating or running out of juice. As we look toward the future of autonomous systems, the choice becomes clearer when viewed through the lens of physical deployment rather than desktop benchmarks. The industry is shifting because the constraints are real and unforgiving in the field. A robot that cannot manage its own heat will not function for long, regardless of how powerful its processor claims to be on a spec sheet. The path forward favors architectures that prioritize thermal efficiency and deterministic performance over raw peak throughput. This shift ensures that the machines we build can actually operate where they are needed most, in environments too harsh or complex for traditional computing standards to endure without constant intervention. The debate is no longer about which architecture wins on a benchmark list. It is about which one enables robots to function as reliable physical agents rather than overheating prototypes. The data confirms that power efficiency and thermal stability are the gatekeepers of autonomy, making ARM the logical choice for systems designed to move, sense, and act in our world without constant human oversight or external cooling infrastructure. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.